Hello, Professor. Today I'll be starting off our presentation discussing about the absolute function. So before we dive deeper into the examples, let's understand the definition of absolute function as well as some other important terms. So an absolute function, it's a function whose function contains an absolute value expression, and the graph of the parent absolute function is the function f of x equal to an absolute function which has a v shape with the minimum point or the vertex at 0, 0. The next slide here, we have the picture of the absolute function as well as some details on the description of the domain being all real numbers and range being non-negative real numbers. To understand more about this, we also need to learn about the vertex of the absolute function. So what is the vertex of the absolute function? The graph g of x, which is equal to the absolute function x minus h plus k, is the image of the function x after the horizontal shift of h unit and the vertical shift of k unit. Therefore, it makes the vertex of the absolute function equal to h and k. To understand more, let's solve a few problems. So we have here the main function being f of x equal x absolute value of x plus 1, which is transformed and denoted by the function g of x. Let's solve A. So the graph of g of x is obtained by shifting the graph of f of x 2 units to the right and 3 units down. We have, as mentioned, the main function being absolute value of x plus 1, and g of x is obtained by shifting 2 units to the right, which we got this equation right here, and 3 units down, making the final equation being g of x equals to x minus 1, g of x equal the absolute value of x minus 1 minus 3. And after graphing the function, we got this graph, which is this handwritten graph, as well as the GeoGebra graph, which we can see here them being the same. The next slide here shows the animation of the units shifting 2 units and 3 units as shown here. 2 units to the right and 3 units down. This will be it for my presentation, and I'll pass it on to my teammate.
Here in exercise B, the graph of gx is obtained by shifting the graph of fx 3 units down. We have the original function, which is fx equal to the absolute value of x plus 1. By shifting fx 3 units down, we need to minus 3 from the original functions, which means that the graph of gx is equal to the absolute value of x plus 1 minus 3. Here is a comparison between hand graph and graph drawn in GeoGebra. As we can see, both of them are the same. Here is the animations of the graph transformations. A here is denoted to the value of graph shifting 3 units down. As we can see, when we move A to the value of 3, the graph of fx will be overlapping with the graph of gx. And when we move A back to 0, the graph of fx will go back to its original positions. In exercise C, the graph of gx is obtained by shifting the graph of fx 2 units to the left and 3 units out. By shifting fx 2 units to the left, we need to plus 2 to the original x value of the original functions, which means that we got gx equal to the absolute value of x plus 3. Then we need to shift the graph 3 units up, which means that we need to plus 3 to the graph obtained above. Therefore, the final functions of gx is equal to the absolute value of x plus 3 and plus 3. Here is a comparison between hand graph and GeoGebra. As we can see, they are both the same. Moving on to the animations of the graph transformations. A here is denoted to when the graph of fx is shifting to the left, and B is when fx is shifting up. As we can see, when A is equal to 2 and B is equal to 3, the graph of fx will be overlapping with the graph of gx. And when both the value of A and B turn back to 0, the graph of fx will be turned back into its original positions.
So let's move on to the example. The graph of gx is obtained by reflecting the graph of fx in the x-axis. We have fx equal to the absolute value of x plus 1, which is gx is obtained by reflecting the graph on fx, which is we got 2gx equal to negative absolute value of x plus 1. Therefore, the function of gx is equal to negative the absolute value of x plus 1. So this is the comparison between the hand graph and the GeoGebra graph. As we can see, it is the same thing and the same pattern. So this is the animation of the graph. As we can see, when we move A, it is reflecting. From fx to gx. So this is the example E. The graph of gx is obtained by reflecting the graph of fx in the x-axis and shifting 3 units up. So we have fx equal to the absolute value of x plus 1. Gx is obtained by reflecting the graph on fx, which we got gx is equal to negative the negative absolute value of x plus 1 and shift 3 units up, which means that we got gx negative value negative absolute value of x plus 1 then plus 3. So therefore the function of gx is equal to negative the absolute value of x plus 1 plus 3. So this is the comparison between the hand graph and the GeoGebra graph, which is the same again, the same pattern. So this is the graph animation. When we move A, it is reflecting, and then when we move B, it has moved three space up to the GX.
So here is the graph of G8 is obtained by reflecting the graph of Fx in the x-axis and shift 3 units and 2 units to the left. So first we have Fx equal to x plus 1 absolute function, and then the Gh is reflecting by shifting Fx 3 units up. So we got Gh equal to x plus 1 plus 2 absolute minus equal to x plus 3 absolute minus. And if we shifting 2 units to the left, then we got gh equal to x plus 3 absolute minus plus 3. Therefore, the function of z equal to x plus 3 minus plus 3. So here is the, if we compare the hand graph and the GeoGebra graph is the same.
So this is the graph animation. If we pull A to the left, it will upside down, and pull B to the right, it will the right way up, and we pull C to the right, it will get the same position.
So in conclusion, after working with this math project, I can understand the graph that can be transformed through various operations like reflecting, shifting, scaling, and stretching. And each operation affects the graph shape and position, and understanding this transformation allows us to visualize and analyze how functions behave under different conditions. And I can also access and process information about the real-world application of graph transformation in various fields like signal processing, motion analysis, optimization problem, and image processing. And last but not least, I can also understanding this concept and can be better assist user with tasks related to graph analysis, interpretation, and application in various contexts.
Thank you for listening to our presentations. and we hope you have a nice day. Goodbye.